Hello, welcome to another problem session. So today we are going to do this problem, which is really on the hard side, but we are going to just follow the definition and process it mathematically to come up with this answer. So physically, what's happening is you have these two containers, and there is no flow between them, and you can consider this to be completely insulated from outside, so these are the only thing we kind of thinking about. And so these two containers, once you let go, the gas will flow, and then the pressure will equilibrate, and the volume will become the double volume of the sum of the two volumes, right? One thing notice is there is no energy flow in or out, which means and since it is an ideal gas, so in an ideal gas, energy is only a function of temperature. So the energy here is the same as energy there. So we can say these were originally at the same temperature, so this will also be on the same temperature. This whole thing will be the same temperature. Okay, so one way to address this is to say what's the entropy here will be entropy of this system 2 at the beginning, and entropy of this system 1 over here, and then the entropy of them together as final. So delta S we are looking for is S final system minus S1 plus S2. So that's the initial and that's the final, which means we need to have a formula for S. If I give an ideal gas in a certain state, what's the entropy? So we need a formula that I have ideal gas, say helium. Okay, I have a helium. I have N, and pressure is P, volume is T, temperature is T. So what's the entropy? Well, we have the formula for entropy is ds equals to TdS equals to du plus P dV. This comes from the first law. And then if you divide by T, is T here and T here. And we can also write this because it's all in pressure, so we can write this in pressure. So this is a function of only temperature. So P over P dV over, you can say PV equals to NKT. So if the T is not changing, then this will be P dV will be minus V dP. So this you can write down minus V dP over T, because things are given pressure, so I just want to write down pressure. We're going to keep working volume, but I'm going to change pressure. Another thing we want to we are looking for is process in its temperature remains the same. Well, even if temperature doesn't remain the same, we could write this guy as maybe n number of moles CV dt over T minus V over T will be number of moles times R over P, so dP over P. And you can see that if I integrate it, so integrate from T equal to 0, then I've got a log T, and I'm gonna end up problem. So I'm gonna say T equals epsilon. Here the problem will be log of P, so P equals to say delta. So from this state to that state, this may be my reference state, and from there I'm gonna have entropy of this, entropy of this, entropy of this, entropy of this with respect to that reference, same reference, so that I don't run into 0. So the S of a state will be NCV log of temperature of the state minus NR log P of that state. And then we have these guys which will be common, NCV log epsilon plus NR log delta. So let's see. Okay, so this will be common in every of the integral. So this is an entropy of a state with temperature T, P, volume V, and so this N, CV, or NR, if you want to write capital N, so this will be same as NK, K being a Boltzmann constant, and CV for ideal gas will be some degree of freedom over 2 times R, and you can again N and R, you can call it NKB. Here we are interested in temperature, temperature being same, so we can say here we can say S equal to, all these guys are all, none of them is going to change, some constant minus N KB log P. So this would the form we're going to use for finding the states of each one of them, right? So entropy of each one of the states. Let me erase and get the clean slate. Okay, so in a sense we know what the starting part is. Using this we know that S1 is equal to, let's call it some constant, we'll just call it some B. So B, which is function of temperature, which is not going to change, so I don't need to P1, and S2 is same B of T minus NKB log P2. Okay, so I have S1 plus S2, that's the starting thing, is some, add this guy 2B of T, and this is common, NKB log P1 P2. So that's the beginning one. So to get this one, I need to figure out, to use this formula, I need the pressure. Well, let's look at, we have a volume here. Volume 1 is N KBT over P1, and volume 2 is NKBT over P2, and pressure we want, the volume is volume 1 plus volume 2 for this guy, net volume. So the pressure we want is going to be N2N KBT. There are 2N molecules now here, 2N, kBt over pressure one is a volume, and this sum of these two guys, so 2 n kBt 1 over v1 plus v2 n kBt over p1 plus n kBt over p2. I think those are the, so n kBt kind of cancels out. I guess 2 times 1 over p1 plus 1 over p2 is 2 times p1 p2 over p1 plus p2. Okay, so when I add this, I'm gonna get S final is gonna be this is temperature is not going to change, so I'm going to just call that is the same, minus nkb log 2 p1 p2 over p1 plus p2, 2 times because there are two n molecules now here, so this n will be 2n. Okay, so now we can subtract, right? So delta S, let me get a different pen, delta S equals to, so this guy will cancel that guy because temperature didn't change, so temperature dependent things all will cancel out, minus 2 n kb log 2 p1 p2 over p1 plus p2, and this is plus nkb p1 p2 log p1 p2. Okay, so if you so if I do this 2 out of here, so we can make it 4, this is square and this is square, and kind of combine them together, so nkb log, and so this is p1 p2, and this will kind of invert, p1 plus p2 is square because this is a minus, so it's going to invert, 4 p1 is square p2 is square, and then we can cancel this, and so this should be equal to nkb log p1 plus p2 is square over 4 p1 p2. So that's the formula that will give us the change in the entropy in this particular problem. Okay, so I know this is kind of like a complicated problem looking, it looks like too many things going on here, but the most important that took place was in the derivation of this formula for a single, so this was a formula for a ideal gas at temperature T. So this was a function of T at temperature T, at pressure P, had n amount of molecules, and of course from there you can, of course, V will be nkBT over P. So V is, you don't need to specify all 4, 3 of them will give you the 4th one using ideal gas law. Okay, I think this is probably it in terms of doing thermodynamics. I was going to do a little bit of kinetic theory. Maybe I'll do a little bit of kinetic theory also, such as Maxwell's distribution, mean free path, and things like that. before I get into electricity and magnetism. Okay, I'll see you in another video. Bye.